In section 2.1, we're going to be talking about a new topic called derivatives and how it relates to rates of change. To start off, let's look at the topic of tangent lines. This is going to be dealing with some curve and the question of what is the slope of the curve. Well, dealing with slope and curves is more complicated because unlike a straight line, the curve does not have a constant slope. So what we do is consider the slope at a particular point along the curve. We call the line which follows the slope at this point and touches the curve at the single point a tangent line to the curve. So tangent lines to the curve thus will follow the slope of the curve as it travels along the curve. So we can take a point on the curve, move it, and draw the tangent line to that point following the slope at that particular point. So the question will be how to calculate the slope and the equation of the tangent line at any given point along a curve. The slope formula can take two coordinates and find the slope of the line passing through those 2 points. However, we need 2 points versus a tangent line which only intersects at 1 point. So we can create 2 points of intersection, x1, y1, x2, y2. That would be called the secant line, intersecting the curve twice. And from there we can calculate the slope of a secant line. But this is the slope of a secant line, not the tangent line. It uses 2 points instead of 1. We can make the change over into the tangent line by considering a secant line to the curve which intersects at 2 points called P and Q. We can let the point Q approach into the point P, getting closer and closer. And as Q approaches P, the secant line will get slowly closer and approach the tangent line. Thus we can say that the tangent line to P is the limit of the secant lines as Q approaches P. And we can actually write it using our limit notation here. So now the computational part will begin to how we create a formula to find the slope of the tangent line. With that in mind, I've set this up here with A and A plus H representing the two numbers along the x-axis where x1 and x2 were located. And as a consequence, f of A and f of A plus H will stand for the y1 and y2. And if I put those notation into the slope formula, m would be equal to f of A plus H minus f of A all over A plus H minus A. And underneath, that would simplify to just H. So this formula here will be used to calculate the slope of any secant line through 2 points on the curve. And here's the key step we're going to take further to introduce the limit. H basically represents how far apart the x1 and x2 are. And so if we let the value of H shrink to 0, we will bring the secant slope into the tangent slope. Hence, if we take the limit as H approaches to 0, this gives us the slope of the tangent line. So we say m, the slope of the tangent line, is equal to the limit as H approaches 0 of f of A plus H minus f of A all over H. Here's a definition then for the tangent line slope. The tangent line to the curve y equals f of x at the point A, comma, f of A is a line through the point with a slope m equals a limit as x approaches A of f of x minus f of A all over x minus A. This is an alternative way of writing the notation I did in the last few slides. So alternatively, I'll often define the tangent line to the curve y equals f of x at the point A, comma, f of A as a line through the point with a slope m equals the limit as h approaches 0 of f of A plus h minus f of A all over h. That's a more common formula that's used for calculating the slope of a tangent line. So let's take an example and find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So when we look at this coordinate in this function, we're going to be using this formula and limit to calculate the slope of the tangent line. So the point we're dealing with here is a comma f of a, in other words. So calculating the slope of the tangent line, I'll do that by taking the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And so we'll calculate that. That'll turn into the limit as h approaches 0 of 1 plus h squared minus 1 squared all over h. That would be equal to the limit as h approaches to 0. If we square that by 1 plus h, it would turn into 1 plus 2h plus h squared minus 1 all over h. Notice how the 1's will cross out here. As a result, there will only be a 2h and h left over in the numerator. We can actually factor out an h to make it into h times 2 plus h all over h. We can cross that out here, and it would turn it into the limit as h approaches to 0 of 2 plus h. And as we've done before, we can plug in a 0 to calculate this. So it would be 2 plus 0 to just get 2. That's the slope of the tangent line at the point 1, 1. To determine the equation of the tangent line, what I'm going to do is use the point slope form y minus y1 equals mx minus x1. Our x1, y1 coordinate will be the 1, 1 coordinate we had up above. M is the slope of the tangent line that we have as 2. So this will turn into y minus 1 equals 2x minus 1. And if we solve this for y, we would get the equation y equals 2x minus 1. So that'll be the equation of the tangent line to the curve of y equals x squared at the coordinate 1, 1. Here's a graph so you can visualize the curve for the parabola along with a tangent line shown here intersecting at the 1 coordinate of 1, 1. We're going to look at another function here, y equals 3 over x, and find the equation of the tangent line at the point 3, 1. So again, as in last time, the point, we can think of it as a comma f of a. So a is the number 3 here that we're going to use. Using the limit definition for the slope of the tangent line, we'll thus be taking the limit as h approaches to 0 of f of 3 plus h minus f of 3 all over h. So what we'll get from this is then the limit as h approaches to 0 of 3 over 3 plus h minus 3 over 3 all over h. So I'll write that down one more time here as the limit as h approaches 0 of 3 over 3 plus h minus 1 all over h. Now I need to simplify this stuff down from this step. What I'm going to do to make that happen is I'm going to multiply both top and bottom by 3 plus h. So that's going to multiply to both terms in the top. So now I can cross out the 3 plus h that's up there. As a result, what we'll have here is the limit as h approaches to 0 of 3 minus 3 plus h all over h times 3 plus h. Now distributing this negative and simplifying up on top, we'll change this into the limit as h approaches to 0 of negative h over h times 3 plus h. And then h can simplify, cross that out from both top and bottom. So from that point, we'll have the limit as h approaches to 0 of negative 1 over 3 plus h. And at this point, it's now appropriate that we can plug in 0 for h. it'll equal to 1 over 3 plus 0, or simply just negative 1/3. So that's the slope of the tangent line at that point. From here, what I'll do then is find the equation of the tangent line, using again the point we had up above, which was 3 comma 1. We'll plug that in to get y minus 1 equals negative 1/3 x minus 3. We'll need to solve this for y just to make it in our more normal form of writing it. We'll get negative 1/3 x plus 1. So solving that will give us y equals negative 1/3 x plus 2. The next topic will have to deal with something called instantaneous velocity. The picture I'm showing here is meant to represent two things, position and time. And so we consider the displacement as the change in position over a certain span of time. And so as the two values for time approach each other, in other words, as h in this case approaches to 0, we're going to be approaching towards a single moment in time, an instant in time. Average velocity using the notation I have here would be calculated by displacement over time, which would be f of a plus h minus f of a all over h. On top we take the difference, which gives the displacement, and a over h, which is the amount of time that's passed. But this is only average velocity. To do instantaneous velocity, we take the limit as h approaches 0 of this. And as h goes to 0, we get to the instantaneous measurement of velocity. Notation we'll often use is v for velocity. So here it says v of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So with this in mind, we're going to look at a situation where an object is dropped from the upper observation deck, which is 450 meters above the ground. And we're going to answer some questions about the velocity that it's traveling. The first thing we need to know is what is the function that gives us the position at a particular moment in time. Position functions are often going to be using the letter s, and that'll be a function called f of t, in other words. The position function for a falling object such as this is 4.9 t squared. This has to deal with the acceleration due to gravity and other things. We'll get more into that later, but for now, we're just going to use this function as the position function for this falling object. So for the first part, we want to know what is the velocity of the ball after 5 seconds. When we say velocity, we most of the time mean instantaneous velocity. So we're going to use our definition of instantaneous velocity at this point with the limit as h approaches 0. I'm going to go ahead and write it as v of t just to change the variable letter to match up with time t in this instance. So it looks something like this. And we're going to use our position function up above, and I'll rewrite it as the limit as h approaches 0 of 4.9 times t plus h squared minus 4.9 t squared all over h. That'll be equal to the limit as h approaches to 0 of 4.9 times t squared plus 2th plus h squared minus 4.9 t squared all over h. We'll of course need the 4.9 here to distribute. So from there it'll change into the limit as h approaches 0 of 4.9 t squared plus 9.8 th plus 4.9 h squared minus 4.9 t squared all over h. And so we should have some things simplifying. 4.9 t squared can be crossed out. We can continue and rewrite this as a limit as h approaches 0 Up on top, I can factor out an h to make it h times 9.8t plus 4.9h all over h. So we can cross out the h here, and it will become the limit as h approaches to 0 of 9.8t plus 4.9h. Now we can go ahead and plug in 0 for h. We'll get 9.8t plus 4.9 times 0 to just come out with 9.8t. So this is our instantaneous velocity function. B of t is equal to 9.8t. For t equals to 5 seconds, like it mentions above, we can calculate v of 5, which would be 9.8 times 5, which is equal to 49. And so that'll be velocity in meters per second. Now for part 2, it asked, at what time would it hit the ground? In order to determine that, we're going to start off by solving the position function for the full distance it can travel. So for it to travel all the way to the ground, that would be 450 meters. I'm going to solve that for t. And so s of t, position, is given by 4.9t squared. So we're going to solve that equal to 450. Now if I divide out the 4.9 from both sides, get t squared equals to 450 divided by 4.9. I'll take the square root. Technically it would be plus or minus, but I really only need to worry about the positive value. And that comes out to be about approximately 9.6. So 9.6 seconds for it to travel the full 450 meters. So what is the velocity at that particular moment in time when it reaches the ground? Well, we have our v of t function up above. So we do v of 9.6, which is equal to 9.8 times 9.6. And that comes out to be approximately 94 meters per second.